let me get started with our introductions. Hi, everyone. I am Ritu Walia, and I'm here along with John Casey. John is our senior software quality assurance lead for the Siemens Digital Industries software. He's leading the QA and testing infrastructure in the integrations team for EDA tools of IC physical design verification. He holds 35 years of experience in this industry and has been through various other profiles and made major contributions. I, on the other hand, work with John in the same team, and I am the software QA and test engineer. So today we are here we're going to present about our paper, QA best practices in GUI test automation for EDA software, that I wrote along with John, who is, and I'm going to mention about which team we belong to in a little more detail after giving some background. The first half of this presentation is going to be covered by lots of talk about the semiconductor industry, which John and I come from. The mention about this industry is in a little more detail so that I can emphasize on the valuable contribution that we software test and QA engineers make to our respective industries. In our case, the electronic design automation industry, which is the full form for EDA in the title, as you can see. So yeah, you're going to hear a lot about the semiconductor industry, some interesting facts about it, and why QA and software testing are an incredibly important part. And if you must have attended the previous presentation by Chuck, he covered a lot of background on test automation, and that gives me a very good to follow up that presentation is great, because I'm going to focus on GUI test automation and the best practices for that. But before that, we're going to talk a lot about the semiconductor industry. So it might feel a little off track, but maybe it's a breath of fresh air. So yeah, let's go along with the flow. So I'm going to start with introduction and some background and about the semiconductor industry that encompasses EDA industry. I will further introduce the EDA software and level of abstraction that it belongs to for further discussing the implementation of the QA techniques that our paper finally talks about. So talking about the digital transformation, we have witnessed major digital transformation in every sector in the past decade, right from automotive to telecom to computing to even fitness. And the technology is only continuing to grow. Moreover, the pandemic has driven unexpectedly high demand for home electronics and gaming consoles, as many people have started working from home and seeking more sources of indoor work and entertainment. There's no denying that our most important and even the most favorite things around include electronics like smartwatches, those noise cancellation headsets, the laptop that's enabling us to attend this very virtual conference, and so on. So, what's that one common thing in all of these electronic systems? Well, if we think of it, it is indeed the semiconductor chips, also called the integrated circuits or the ICs or the chips, simply as we call it. These chips operate and peak from under and inside a smart speaker, locked deep within a phone, inside data centers, you name it. We can safely say nearly all of us now live in a semiconductor-centric world full of digitalization, and the beating hearts of this digitalization are indeed the semiconductor chips. Speaking of which, here are some stats. The figure here shows semiconductor demand by end use, which, as you can see, is extensive in various sectors. It is mentioned in billions of dollars, especially as per the 2020 stats. Sale in computer sector has drastically increased as COVID-19 spurred more remote work in schools, and it contributes majorly, as you can see, in other sectors as well. Further, there is one more bar graph that focuses on the contribution specifically with respect to the US market. The bar graph here shows the global market share in chip sales. And the US semiconductor industry has nearly half the global market share and is continuing to display steady annual growth. So you can only imagine what kind of contribution are we making in the entire world. So now, how exactly is the semiconductor industry related to the EDA industry? Let's see. The figure on the top right shows that it all starts with the customer specification. And finally, we end up obtaining the next generation device. All the in-betweens, at least for the semiconductor part, which is mentioned in the on the top part of the arrow of the supply chain, it includes the EDA tools, formulating of the EDA tools, having a design data in place, designing and verification processes, and then finally getting the chip manufactured. This process is a result of a strategic collaboration between the design company, the manufacturer, which is also called the semiconductor foundry, and the EDA vendor. At the bottom, you can see a correlation diagram that shows one triangle of semiconductor industry related to the foundry, and those are related to the EDA vendor. Further, the semiconductor industry even collaborates with other sectors like the embedded systems, which further collaborate with its respective foundry and also the EDA industry. So, this is an entire collaboration that ultimately works together to provide us with the most high tech systems. The semiconductor design company uses EDA tools, in our case, for the IC design, verification, and implementation processes, and log a final tape out that gets sent to the foundry for manufacturing. And the foundry as well uses EDA tools for various post layout processing. Well, so this makes me jump to my next topic, the EDA industry. So, what are these that I'm talking about? And I've said like a million times now. Broadly, these are software tools used for designing and manufacturing electronic components like ICs, electronic systems like PCBs, and all the system level designs prior to the practical installation. Well, here's a little background. At the early stages of chip design, in 1970s, chip designs were done by hand. The designer would draw the design on paper. This paper design would then be transferred on a photo mask, which is a physical material. It's made of a material called rubylith. Just like how negatives of photographs used to be converted into the physical copies. The photomask would then be used to produce the chip designs, patterns on the substrate, which is again a physical material. This is done by projecting light through the mask onto a material and so on. But as these chips got increasingly more complex with more transistors and connections, simple software tools were developed in-house by big design companies to aid in their designs. These tools would become the EDA software that are used today. Hence, EDA includes tools right from the IC level to the system level. As modern semiconductor chips are made up of billions of components, these EDA tools have become one of the essential components in designing. Due to such huge design requirement and complex semiconductor processes, various EDA tools are categorized into various platforms to perform these different processes. These advancing processes also demand platform interoperability, meaning a strong integration between various EDA tools. One of these categories is the physical design and verification, which, as you can see from the bar graph, contributes majorly to the US EDA market, the one mentioned with red in color. So I'm going to talk more about the IC physical design and verification processes because the team that John and I belong to, we come from this particular product category. And in the next slide, I'm going to briefly discuss the impact of the EDA tools. So the figure on the right is just for a little fun how logic circuits convert into the end consumer utility, which is a very old game called Pong. So in this slide, I can safely say that the semiconductor industry has got a serious boost with the emergence of EDA, especially in supporting something called a technological scaling. So technological scaling refers to shrinking of the length of a transistor gate, at least in most cases until the recent past, and there's a quest to reduce the size of the chip to achieve the power, performance, area, and cost goals. And EDA tools make major contribution in supporting this scaling. There's a huge surge in the need for complex ICs. Complex ICs such as CPUs and GPUs may consist of hundreds of cores, terabytes of memories, and multiple high-speed communication channels, requiring increasingly sophisticated EDA tools to help them. The EDA vendors have to ensure they have a strong enough foundation to be able to offer engineers tools that fit their workflows across any of these scenarios, delivering just the right amount of EDA functionality. Therefore, performing QA on EDA tools, um, uh, Caliber real-time platform tools in our case poses various unique challenges. So I have given this entire background to emphasize that we are going to talk about some complex processes and how the most basic and traditional QA techniques help us overcome them. So before some background about Caliber Real-Time, let's see what product category is it involved in. I'm going to talk a little bit about IC physical design and verification as mentioned before, which are integral aspects of the IC tape-out. The physical design, implementation, and verification processes involve the literal physical layout of the logic circuit, just like the logic circuit that we saw in our previous slide. And all of these involve literal physical layout, the wiring between them, and the memory circuits. And all of these are embedded on a single chip. When you have thousands and millions or even billions of such circuits, the layouting can get very difficult, leaving a scope for numerous errors. Moreover, the increasing complexity of ICs due to high demand for compute-intensive technologies like AI, IoT, and machine learning have boosted the demand for advanced EDA tools for validation of the IC layout accurately. The verification tools precisely validate densely populated ICs to verify the designs with the expected requirement, such as something called a design rule checking, which is the full form for DRC. We're going to talk a little more about DRC further. In today's nanotechnology, physical verification has become a crucial stage in the processing of extremely complicated and compact designs. In the graph here, or in chip designing in general, there is something called a technology node, as you can see on the x-axis. Technology node refers to the technological scaling that implies that the smaller the gate, the more processing power that can be packed into a given space. So this growing trend of miniaturization of IC on the x-axis, as you can see with the growing miniaturization of IC, the overall cost of the chip production is increasing. And as you can see in blue here is the verification cost, which is almost as equal as the design cost. Hence, I can say that this miniaturization of IC have increasingly propelled the market value of physical verification processes, which is as expensive as the design process. Hence, now I talk about the product that John and I work on, and it's the Caliber real-time interfaces that contributes towards implementing the previously mentioned processes and that helped us deduce the QA techniques discussed in our paper. The purpose of Caliber real-time platform is finding flaws in an IC design and layout prior to manufacturing that can save the design company and manufacturer billions of dollars. Designers need to ensure that designs adhere to the manufacturing requirements. Since these designs may include billions of logic circuits and interconnects, the verification checks need to be run at steps of the design and implementation process, making it computationally intensive task. Real-time overcomes these computational challenges, for example, reducing verification time as shown in the diagram here, with and without real-time. And real-time does that by introducing the Caliber real-time digital sign-off DRC component that can be integrated in the physical design implementation flow with the external tool. This way, it successfully delivers instantaneous rule checking whenever required. Rule checking or the design rule checking or the DRC in itself is a process that engineers use to determine if physical layout of the chip design complies with the manufacturing requirements. Hence, I can summarize by saying that real-time performs DRC to determine the validity of design and physical implementation against the design rules. It reduces verification iterations and overall design time. It enables the design optimization during creation of layout. And I'm very proud to say that real-time was the Electronic Design Magazine's Product of the Year in 2011. And also in previous 10 years, since past 10 years, real-time has never had to issue a patch due to a regression in its functionality, which is great and which makes this product a great example for implementing our QA techniques and discussing it and sharing it further. So the figure here shows the flow in one of the interfaces, and it saves significant verification time. GUI, a graphical user interface as we know, is one of the major components of the Calibre real-time's implementation. Hence, my further focus will be on talking about GUI testing. Well, one of the interesting parts about my work as a software tester has been GUI test automation for performing QA on the Calibre real-time platforms. EDA tools enable designers to work with the GUI as well as their command line interface counterpart. The figure here shows an external layout design implementation tool. And the highlighted box shows the real-time digital toolbar. This toolbar is an interface that is tightly integrated with the external tool, enabling designers to use real-time operations through the GUI. Also, as we know, input to the GUI consists of sequence of events which are generated when a user interacts with the GUI elements. The number of possible permutations of these events lead to a large number of GUI states. Therefore, GUI may be highly subject to change in the form of enhancements and fixes. This increases the need for repeatability for verification of these tasks. Therefore, this makes automation an integral part of the testing process. This way, GUI testing, its automation, and regression testing are important parts of my job. Therefore, in our paper, we discuss QA challenges relating to GUI testing and test automation that may be unique to the EDA industry and give some examples using the Calibre real-time interfaces. But most importantly, we emphasize that even the most traditional and basic QA techniques derived from years of experience, if implemented correctly and effectively, can help overcome most complex processes, just like those required for software testing in the complex EDA industry, as you've seen before. I hereby invite John to take over and elaborate a little more on QA challenges and resolutions to those, giving examples from the EDA industry.
Yeah, thank you, Ritu. I've been working in the EDA industry basically since the beginning for 35 years. And I distinctly remember in a lot of cases where people would draw circuits by hand. And back then, you didn't even have to be a technical person to do that. There were a lot of people with non-technical backgrounds drawing layout. It would just be an exercise. They would think of it as a puzzle. Someone would give them a set of rules about how far apart shapes could be and what shapes could be placed onto other shapes. And they would figure out the smallest area to draw those shapes in and actually draw transistors and resistors and capacitors and different data types without even really knowing what they were doing. Well, today, that's been now done in an automated fashion for quite some time. So today's software environment, EDA software environment, is really a complex set of graphical tools and non-graphical tools. And these tools interact with one another and inherit data from one another in a pretty complex design flow. Also, the tools involved in the design flow can be from different vendors who specialize in those tools. And there are different tools that customers use depending on whether they're designing a digital circuit or an analog circuit. So if they're designing a GPU or a CPU, they'd perform the creation in a digital place and route tool. And if they were designing an analog circuit like an op-amp amplifier, then they would use a different set of tools, a custom layout tool. When building and forming QA on these tools, a testing framework needs to be developed that is flexible enough to send data back and forth between any application and drive the behavior of the graphical tools involved in an automated fashion. In EDA, the tools are primarily built and run on a Linux operating system. Before Linux, there was the Unix, various operating systems, Solaris from Sun, AIX operating system from IBM, and even more before then. There are different Linux flavors that need to be supported and multiple versions within each flavor. Therefore, the testing network we built at Siemens has been constructed using a highly portable and flexible set of shell scripts and Perl and Tcl programs that interact with one another and the tools themselves. The use of these standard shell scripts, Perl and TK, were intentional because they're freely provided with all Linux environments that we support and are generally portable between Linux OSs. In the case of our specific product, Calibre Realtime, it must be tested while integrated with 4 different IC analog layout editors and 3 different IC digital layout tools. These are called place and route tools. Some are made by Siemens and some are made by other vendors. It was imperative that we're able to communicate with those tools and have a way to interact with their event loops and drive them synchronously using our regression scripts. Linux sockets were the most efficient way to communicate between these processes. Most interactive tools in our industry have a way to communicate through a Linux socket, and through that, we can send them their own API commands to drive their tool synchronously. Some of those tools, though, do have interfaces in other languages other than our scripting languages, so we've had to do a bit of translation between our language and their language before sending the commands through the socket. Go ahead, next slide. So the EDA tool testing strategy must really be carefully chosen. It's just due to the infinite number of different layout designs that an engineer could create and an infinite number of combinations of fabrication rules that could be imposed by the chip foundry. Because you don't have infinite time to test our software, we decided we should focus our effort on how the IC designer really uses the tool. The QA engineer to take on this role must be educated in the way the IC design engineer works, what they're thinking about when they use the tool and the common design scenarios they create, and based on that, decide which scenarios would be worth the effort to test and which would not. For example, most photomask shapes come in certain rectangular or combinations of 90-degree shapes, orthogonal shapes. So does it really make sense to spend a lot of QA resources creating an infinite number of bizarre test cases and with shapes with 10,000 edges to it? Another example is when the GUI asks for a photomask, a layer name. Should the entry field for that consider any layer that's possible or a specialized layer that would only be valid in that context? It's worth the investment, really, we think, to make sure the QA engineer knows how the customer uses the tool, is very well versed in all the use cases, and is familiar with the overall IC design process, and is not just testing randomly. Also, in EDA software, there may be different GUIs that can be developed using different graphical packages and languages. It's vital that the QA tester be aware of and become proficient with these languages to detect potential problems. For example, a tester should understand the special reserved character set in each implementer's language in order to find errors that might occur due to those special characters. For example, in Tcl a square bracket is a special reserved character that, if not processed correctly after entry into a form, it could result in an execution error. Understanding the syntax and possible limitations of each language has really helped us uncover programming errors. It's definitely worth the investment, we think, to not only make QA engineers proficient in the basic script writing of the software package, but also the philosophy and nuances of that package. So right here is an example of an error found because the tester understood the underlying software package used to develop the application. Because the tester understood that curly braces, in this case, are reserved characters in Tcl, sending a string where curly braces are mismatched caused an application error. In all languages, there are different sets of reserved characters, of course, and QA engineers should be aware to make sure that the developer did not make a programming error processing that data item. Here's an example of knowing how an application is used by the customer is important to determining whether that operation is correct or what is displayed is correct. The QA engineer must understand what is being displayed, the purpose of it, and the relationships between data items that are displayed. For example, what is selected in the design rule checks on the right side depends on what is selected in the layer list on the left side. The relationships determined by Foundry rules that determine how close shapes on the layers can be from one another and other factors. The QA engineer, when they understand this, can analyze whether it's a bug or these boxes to be checked or not. Investing in the QA engineer's understanding of the whole IC design process and what is expected when viewing the data has been very crucial for us. Because IC design is a complex process, the wording in forms can mean different things to different people. In the form pictured here, it shows that 150 polygons were detected, but only a few shapes are shown on the screen. In this case, the QA engineer has to understand the relationship of elements in the GUI to determine if the form is correctly shown. In this case, the wording is a little misleading, but not really a bug. Because IC design layouts are built using a hierarchy of layout cells, and these underlying cells can have their own polygons hidden by default, the polygon count in this case includes the polygons in the underlying cells, which you can't see visually, but they're there, and then these do add up to 150. In this case, the QA engineer must ask the developer whether they intended to warn the customer due to the polygon count being exceeded for this particular cell or for the entire design. As with most complex products, errors must be caught quickly. In EDA software, the bug may not be in the product you're assigned to test, but in an upstream product, which may be from a different vendor. Therefore, we have determined the best ways to build our entire integrated product every hour to track changes, every day for QA to test, and have the engineers working on the product run the entire regression suite each time they check in new code. Of course, it does help to have an integrated network of available machines to run tests on, which we do, and this then may not be applicable to every environment. We found that with the Calibre real-time product, that the strategy outweighs the possible slowdown of the development activity. With nearly hourly software builds and logging of changes for each build, the check-in of the offending code that caused the bug can easily be identified. If a third-party tool version is changed, that impact is also determined rapidly, including performance changes. And with the developers themselves running regressions before check-in, bugs are caught by the developers themselves prior to QA even testing the build. Of course, this does require our QA engineers to keep all regressions up to date on a daily basis and to perform fast turnaround of required regression changes such as baseline updates. This also requires an effective bug and engineering activity tracking system, which we do employ, and QA is also involved, like the Jira product from Atlassian. We found that having smoke tests or system stability tests for developers to run prior to running the main set of regression tests also helps with the turnaround time, as the smoke tests really determine whether running the full set of tests would be valuable. So smoke tests usually last for a minute or two, maybe a few minutes, but kind of give a system stability check. So when dealing with third-party tools, especially layout editors, it became fundamentally important for our product to adapt to the ever-evolving nature of these tools. Between versions of these tools, window sizes change, forms change with different content, and many operations change their behavior when done interactively. Even within the Calibre real-time product, this has been the case. It was important for us in QA to adapt to these changes by employing the use of APIs that, for example, obtain the current window size or execute forms without clicking at specific XY screen coordinates. we've had to develop our own set of testing APIs that are not dependent on graphical coordinates. We have had to, while many automated tools operate by outputting replayable transcripts at very specific coordinates, we found that re-implementing or regenerating tests every time a graphical change was made into a form was not very practical. It was much better to build a structured and layered set of API commands that are not XY dependent. For example, entering text in a form of this type with a specific label, and it automatically calculates the proper position based on the form dimension and identifier for the label, and automatically enters the text at that position. Also, test writing is not efficient when always having to enter data into graphical forms. Therefore, the use of testing APIs, in which there are just individual function calls to do the same functionality as one would do interactively, has helped us with our productivity. For example, instead of clicking on the Run DRC button that Ritu showed in the picture of our tool, on that toolbar, we've asked our developers to provide us a Run DRC API call that will not only run the design rule checker, but also wait for completion so the call can be run synchronously. It's even better if, after the development of APIs, those API commands could be automatically written to the test log or the tool log during interactive operations so that the basics of a QA script can be captured automatically. To summarize, we recommend asking your developers or management, if you need to automate testing of a graphical tool, to invest in developing testing APIs and replayability. We found that this to be beneficial not only to QA, but also to customers of the product. And with that, I'll go ahead and turn it back to Ritu.
Thank you, John, and thank you for keeping us on track with time. I am going to quickly move forward with talking about a couple of more challenges that entails and with respect to the EDA software. So, complex customer data. Well, complex ICs such as CPUs and GPUs can have hundreds of cores, and the foundry fabrication rules can be extremely different between different customers. Furthermore, many EDA customers customize their design tools to fit their own particular needs, as most environments need to support custom data entry forms to tailor the needs of a designer, of a particular engineer. Therefore, with Calibre Real-Time, it was very important for us to include customer data in our regression database, including tool customizations. Having a test suite with very simple test design can only cover a small fraction of what is important to our customers. For example, the two cells at the top of the slide represent a very simple layout design on the left and a more complex one on the right, as you can see. We have found that for customers working with huge designs, it is worth the investment to get representative data from them that they would use the tool on and use that design in the performance and capacity regression tests. Even our functionality tests often use pared down versions of customer data. We have also openly asked customers to share their customization code, and they have almost mostly provided that for us because, well, QA is so important. This guarantees that not only the functionality that they use is tested from release to release, but also their custom code, which is just as important to them. Lastly, in the Calibre real-time application, we found that it is also a requirement that sessions be active for multiple days without closing the tool. This is due to extensive time needed to load design, having hundreds and millions or even billions of layout shapes. Therefore, it is important for us to develop stress tests where we simulate designers working on tools. So, we track the CPU and wall-time performance as well as memory consumption to verify there are no slowdowns or memory leaks. These tests run analysis in random areas of a complex customer design for a prolonged period, as shown in the figure at the bottom, wherein a tickle script is obtained to run analysis on different random areas on a customer design. Therefore, it is important for us to develop stress tests where we simulate a designer working on the tool for multiple hours, sometimes even days. And so far, we discuss some QA challenges and what's imperative for their resolution. There are various other important additional testing techniques like the boundary value analysis and exploratory testing, as we know. As mentioned before, performing boundary value analysis for numerical entries and length of the string in forms based on data type being entered is a necessity. But in addition to this, there are times when the third-party tool being integrated with the Foundry design rules contain their own set of value limitations, and these can be different between different vendors. Therefore, boundary value analysis require these checks as well. For example, a layout design tool may have a limit on the length of a layer name, but not for the analysis tool. So your tool may not get a buffer overflow if a particular name is being entered, but exporting the design from the layout tool might. QA testers must be mindful of these and run any changes through the entire design flow before approving it. One of the testing techniques that is especially useful in testing EDA software is exploratory testing next. Once a bug is found in a particular area of design flow, it will likely affect the other aspects of the design flow. So it is often wise to use exploratory testing in that area. For example, if there is a particular problem in exporting a design for one purpose, such as running the layout design rule checking tool, that same problem is likely to exist in the tool that compares layout versus the logic circuit, which is called schematic. So that must also be checked. The QA testers need to have the freedom to explore other areas beside the area under test to find additional bugs. So to summarize, it becomes extremely important to invest time in developing QA expertise in chip design domain and use that to guide testing of the individual tool and the whole design flow. This also includes developing QA expertise in software packages used and use that knowledge when testing data entry. It is also very important to develop a portable, flexible QA scripting framework designed for inter-process communication and hiding of graphical implementation specifics. Performing hourly builds of the software, daily QA regression runs, and analysis and updating of regressions are also incredibly important. Well, we have to keep a check on process from the developers running the regression prior to the check-in of the software changes also. So yeah, a QA tester should be mindful of that as well. And lastly, it is also wise to perform boundary value analysis, keeping in mind the whole flow and encouraging exploratory testing by testers. So to summarize, we largely emphasize that even the most basic and the traditional QA techniques, again, if they work incredibly awesomely to overcome the QA challenges in a complex environment, then the common QA testing techniques can be implemented, if implemented effectively, can do wonders. And that's about it. If you have any questions, I know there is a time crunch. If you have any questions, please reach out to John and I through any of the platforms, and we would be glad to answer any of the queries. Thank you so much.
And thank you, Ritu. Thank you, John. We are a little bit over time, but we've got a break right now, so I think it's probably okay if we're a couple minutes over. There was one question in the comments. Michael asks, Tickle TK has a very nostalgic spot for me, as I used it back when I controlled Cisco routers and switches. Do you use expect along with it?
I'm sorry, can you be a little louder? I'm just trying to pull out the chat box, Ivan.
Yeah, he's asking if you use a tool called expect along with Tickle TK.
Oh, for our framework? Yes, John.
Yeah, no, we do not. We use Tickle TK extensively, both scripting and for custom forms, but yeah, not that tool.